Hi everyone, my name is Corentin Dumry. I'm a PhD student at EPFL in Switzerland, and today I'm here to talk about our paper counting stacked objects. Computer vision has always struggled with scenes that are very complex or very cluttered. Yet stacked objects are everywhere in our lives, be it the products on the shelves at the supermarket, the food in our plates, or just random items in boxes. All these are visually very complex and largely ignored by recent 3D scene understanding or counting methods. Yet, if we could at least count the objects in these stacks, it would already be very useful. We could answer questions like, is this box ready to ship? Or how many calories am I about to eat? Previous works in object counting have only attempted to count visible objects, and even then, most of the time they only focus on easily separable objects. But when we try to use them on visually complex images with cluttered objects, the results are clearly not as good. Many objects are missed, especially the ones that are partially occluded. That's why in this work we introduce a method to count stacked objects, which includes the objects that cannot be seen directly. To train our network, we also release a large-scale synthetic dataset, as well as a real evaluation dataset. We hope these contributions will allow the community to improve computer vision at these challenging applications. So formally, in this work, we aim to take as input a set of images of a stack, potentially in a container or in plastic wrapping, as well as the associated 3D cameras in metric units. If the object is new, we similarly capture a set of images of a single object. Then we aim to output n, the total number of objects in the stack, including the ones that are not seen and are occluded by the object on top. However, predicting n from images alone proves to be highly challenging for several reasons. First, machine learning models struggle to make sense of 3D stacks from only 2D images. Second, we don't have any large-scale labeled data, and counting these stacks can be very time-consuming. Therefore, we will first need to reformulate this problem to make it easier to solve with computer vision methods. So what can we do? Well, if we knew the volume of the container, VC, and the volume of a single object, VO, we could get a good estimate by computing the ratio. So if you have an object of volume x and a container of volume 1000x, then you'd expect to fit approximately 1000 objects in a container. However, that's not quite true in practice. You'll observe, for example for this shape, that you can only fit around 400. So why is that? Let's have a look at a slice of this stack. We see that actually an important fraction of space is not occupied by the objects, but by the gaps between them. In fact, if you were to compute the fraction of space occupied by the objects, you would find that it is around 41%. In this work, we denote this fraction gamma and refer to it as the volume occupancy. In our early experiments, we observed that gamma tends to be very shape-dependent. If we consider these three shapes and again visualize a slice of the stacked objects, we can see that the fraction of space used by the objects varies significantly. With a small approximation, we consider this ratio to be constant within a stack. One of the key insights of our work is that this volume can be predicted from an image of the stack. It is much easier, in fact, than attempting to predict the total count n directly. Intuitively, if objects deeper in the stack remain visible, then the gaps between the objects are substantial and the percentage of volume they occupy is low. Oppositely, when only the top layer is visible, the volume occupancy tends to be high. This does not depend on the exact shape of the objects being observed, and should in theory apply even to new inputs with shapes unseen during training. So that's the key idea in our method. We integrate the ratio gamma into this simple formula, which greatly improves the accuracy of our predictions. We multiply the volume occupancy gamma by the volume of the container, and divide it by the volume of a single object. Now we'll need three components to evaluate this formula: a network to estimate gamma from an image, a method to measure volumes from images for VO and VC, and large-scale labeled synthetic data. So our input images will typically look like this example picture. Ideally, we would use such images with ground truth count to train a network to predict gamma or even the total count directly. However, there is no such data, and it would be unthinkable to try to collect such a large-scale real dataset. So we'll see in section 3 how we produce large-scale synthetic data with ground truth gamma and count. However, if you look at one of these training samples and the real image side by side, they look quite different, and this significant domain gap would hurt performance when we apply the network on real data. In order to minimize this domain gap, the first thing we'll do is to get some segmentations of the container and of the objects, which are very easy to get using SAM2. We use these segmentations to identify the frame where the objects are the most visible, and crop the image around those objects. This gives a good overview of the stacked objects, typically from the top of the stack, although it doesn't need to be. It already becomes harder to distinguish between synthetic and real data. However, it is still possible to tell them apart, which means there is still a significant domain gap. In order to further reduce it, let's look more closely at the training data. In this figure, I have sorted the scenes by ascending gamma from left to right. It looks coherent, but if you were to feed these images to a network and train it to predict gamma, it would still be a fairly challenging task. Instead, let's have a look at the depth maps of these images. Now it is quite clear that lighter depth maps, in which you can see further down the layers, tend to correspond to stacks with lower volume occupancy gamma. So with this observation, we can take the depth maps of both images instead. These depth maps are very easy to compute with modern monocular depth estimators, and now the domain gap is non-existent. Intuitively, gamma should be rendering invariant. As we just said, the volume occupancy gamma can be predicted from the depth maps, so we don't lose any accuracy, and this makes the task significantly easier for the network. Finally, regarding the network itself, we use the DynoV2 architecture and add a regression head to make it predict a scalar. This comes with the added benefit that DynoV2 is pre-trained on real data, so even though our final model is only fine-tuned on synthetic data, it has still seen large amounts of real data during its pre-training, which further helps bridge the domain gap. The next component we need is 3D volume estimation. To achieve this, we develop a simple method based on 3D Gaussian splatting. We isolate the stack to reconstruct it, and then measure the volume of the 3DGS model by voxel carving using the depth maps from 3DGS. The final volume in metric units is then computed from the number of remaining voxels. In most applications, the volume of a single unit is already known, but if it isn't, we estimate its volume from a separate set of images. Then this volume can be reused in many different scenes containing that same object. Finally, the last component we'll still need is training data. It would be unthinkable to attempt to collect enough real data to train a network, given the complexity of the stacks. Furthermore, it would be highly challenging to measure gamma in real scenes. So to achieve our goal, we have developed and released a large-scale synthetic dataset comprised of 13,000 physically simulated scenes. The simulation is performed in Blender by taking random shapes from the ABC dataset and dropping them in batches in a randomly selected container. Then we render all these boxes from multiple views and with different materials. All renders use ray tracing, which is crucial here to ensure that objects in the lower layers of the stack appear darker due to occlusions from the upper layers. Finally, we digitally measure the ground truth count and the volume occupancy gamma. We also save segmentation masks and ground truth depth maps. Finally, let's see some results. For this paper, we released a dataset of real stacks with ground truth counts acquired manually, either by counting by hand the number of objects in each stack, or by deducing it from the weight of the stack when the number of instances is above 500. So I'll give you a bit of time here, and I'd like all of you to take a second to look at this image and try to guess how many M&Ms are in this little cup. Think of a number in your head. All right, the answer was 36, and our model predicted 38. Now, same thing for this box of beads. How many are in this box? And the answer was just a bit above 1,800, while our model predicted 2,100. Our model is fairly accurate, with predictions that are often within 10 to 20% of the real ground truth count. And finally, for this smaller box of beads, take a second to think. And the answer was exactly 300, while our model got 261. We also ask a panel of participants to guess the number of objects in each scene of the dataset to evaluate just how good humans are at this task. This allows us to define two new baselines. First, the average error of all humans, and second, the error of the average prediction, which of course is a much better estimate, as human errors tend to cancel out. In our experiments, our method in dark blue here outperforms humans by a wide margin. It also performs better than the human average baseline, which, as expected, is already a lot stronger than the guesses of a single human. Finally, we also experimented with a vision language model, but it performed worse than every other baseline. We also performed an ablation study in which we train another similar network, but taking RGB images as input instead of depth maps. As expected, in light blue here, this leads to a drop of performance when applied on real data. Finally, I just want to say that our datasets are already released and can be downloaded from the project page of our paper. This includes a 3D synthetic dataset with ground truth geometry count and gamma, and a 3D real dataset with ground truth count and human estimations. Thank you for listening. I will be giving the same presentation on October 23rd at ICCV, and the poster session will be on the same day from 2:15 to 4:15 p.m. So feel free to come ask your questions there. And if you have more, the code and datasets are already released, but also feel free to reach out. Thanks again for listening.